So we have looked at mixing chamber. That's where you mix two liquids or two gases. And we have done that. There's one assignment. There's one question in your assignment that involve mixing chamber. Okay, that's mixing chamber. Let me try to write something on it. The mixing chamber is very easy. You have the turbine. Okay, this is the turbine. The turbine is supposed to change work into electrical energy. Whatever the turbine is supposed to have some how I'm going to say it. Well, the turbine is really actually converting work to electrical energy. That's all. That's all what turbine is all about. A nozzle. If you look at this, a nozzle is supposed to reduce the pressure. If you look at this diagram, over here the diameter is very large. Over here the diameter is smaller. So you increase, not reduce, you increase the pressure or you reduce? Come on, somebody. Is it increasing or reducing the pressure?
It's increasing.
Increasing, right. Yes, I said it wrongly just now. A nozzle is supposed to increase because the surface, the diameter is smaller. So that means the surface area is, the diameter is smaller, so it should increase the pressure. And if you look at the diffuser, you have a bigger surface, a bigger diameter at the outlet. So that means your pressure should be less. Okay? Compared to the nozzle, your diameter is smaller at the outlet, so your pressure is increased. If you look at the diffuser, you're supposed to decrease the pressure. So that's about pressure. Throttling valve also supposed to reduce the pressure. A throttling valve, sorry. Now let's look at compressor. Compressor is you compress the gases. That means you increase the pressure. A compressor, you compress the gases, so that means you increase the pressure. Now, the next equipment is the heat exchanger. There's two inlet, two outlet. This is the inlet, one of it. There's another inlet over here. Okay, there's two inlet over in this heat exchanger. Just like the name implies, it exchange heat. Okay, let's say the fluid coming in here is a hot fluid. That's hotter than the fluid coming from here. This is a cold fluid. Okay, this is a cold fluid. So when you have two fluid that has two different temperatures, there will be heat exchange going on. Even though they are not in direct contact, for example, this fluid is flowing inside the tube. It is not mixing with the outer fluid in the chamber here. So there's no direct contact. Okay, so this fluid in the chamber here, we refer to it as the shell fluid. So it will exit at the bottom here. And the fluid that is flowing inside the pipe will just flow along the pipe without any contact with the hotter fluid, and it will exit on the other side of the pipe, which is here. Okay, now let's say this hotter fluid is a steam. Supersaturated steam. It's supersaturated steam. Okay. T in. Let me try to get this. How I'm going to do it. Okay. Superheated steam. This is superheated. It's very, very hot. Okay. And the fluid that you want to heat up, the cold fluid, should has a temperature that is much, much lower compared to your superheated steam. Oops. And that's your superheated steam. And this cold fluid should has a very low temperature. And since this superheated steam is hotter, so that superheated steam, if I can change my color of the point, the marker. Okay, now the superheated heated steam is hotter. So there will be a transfer of heat from the hot fluid to the cold fluid. So there will be heat coming into the pipe. The heat transfer going into the pipe. So what happened is the fluid that is inside the pipe will get heated up. So by the time that fluid comes out, by the time that fluid comes out, it should be hotter. This temperature, oops, sorry, I can't seem to be able to get, okay. This temperature here coming out, this out temperature compared to this in temperature should be higher. The out temperature should be higher than the in temperature. The out should be higher than the in temperature because the hot superheated steam has transferred its heat to the fluid inside the pipe. So what happened to the hot superheated steam when it comes out here? It should has cooled down. The temperature should be lower than the hot temperature inlet. The T, let's say, this is T hot in, coming in, the superheated temperature. This is T hot out. That T hot out should be less than the T hot in. Okay, let me write it over here. T hot out should be less than T hot in, because the temperature, there is heat transfer from the hot fluid to the cold fluid. Okay, guys, do you get what I'm trying to say? Any response? Anybody? Am I speaking to myself?
No, doctor.
Yes, Dr. Clear.
Thank you, because I need some sort of responses from you guys. I thought I unmute myself just now. Okay, that's very important, because when you look at heat exchanger, if you look at the flow of heat, is from the hot fluid to the cold fluid. There's no heat exchange between the surrounding with the heat exchanger. There's no exchange of heat with the surrounding at all. So that means your Q, which is the symbol for heat transfer, let me put a dot there, for the hot fluid should be the same as the Q being received by the cold fluid. It should be the same. Okay, because the transfer is only between these two fluids, which is the hot and the cold fluid. So if we did not, just now we put this, let me write C there for a cold fluid. So there's a C there. Having difficulty trying to write using PowerPoint. So this should be a cold fluid. Okay, T cold out, T cold in. So the hot fluid, the heat from the hot fluid will be transferred to the cold fluid. That means whatever Q being given off by the hot fluid is going to be received by the cold fluid. Okay, the heat transfer is only between these two fluids. There's no heat exchange between with the surrounding at all. So whatever heat transfer you calculate for the hot fluid should be the same that is received by the cold fluid. Okay, there's a question at the back of the chapter 7. If you look at the 3rd edition, there's one question on heat exchanger. Where is it? Is it 728? Yep. There's one question, 728 in the 3rd edition. I'm not sure in the 4th edition what's the numbering, but that's one of the question on heat exchanger. So have a look at it, try to solve it. It's problem 728 in the old 3rd edition textbook. Okay, let's go to the next slide. I think the next slide is all about, okay, increase the velocity as the expand. Okay, you I think you understand that. I already explained that. Okay, reduce pressure. Okay, turbine. You produce work that is going to be changed to electrical energy. Compressor, I already mentioned that. This is heat exchanger. Okay, that's it. So we're going to proceed to mechanical mechanical energy. Let me try to get the slide. Not mechanical energy, sorry. Mechanical energy balance. Oops, where is my slide for mechanical energy balance? Okay, let me escape this. Hold on, guys. I need to open my slide first because I already uploaded it in e-learning. Okay, so you guys should have a copy of it in e-learning. Let's show this. Let's share the slide with you guys. Okay, guys. If you look at the equation here, the equation that I'm pointing using my cursor now, if you look at the equation, there's some term that you are familiar with, and there's a few terms that doesn't look the same as it doesn't really they are quite familiar to you. So the terms, the nomenclature you are familiar with, but they are not the same. The equation is not the same as what we have looked at for a closed or an open system. For this mechanical energy balance, it's supposed to be an open system. Okay, it's supposed to be an open system because your fluid is coming in and coming out. So when you look at mechanical energy balance, you'll be dealing with fluids. Let me get my pointer. You'll be, oh dear. You'll be looking at fluid coming in and out. You either have a pipeline or you have a tank. Some fluid is definitely coming in and out. Okay. So over here, this is the final equation for your mechanical energy balance. You simplify this first equation to the, oh dear, there's supposed to be, let's see, why is there a plus sign there? Why is that plus sign? Anyway, from this first equation, you simplify it to this second equation. This term is referred to as friction loss. That is from this whole bracket over here. You just give it a symbol of friction loss. The F with the cap is the friction loss. The friction loss can only be obtained experimentally. So it should be given in the question. And normally it's assumed zero. Friction loss is due to the friction of the fluid with the pipe wall. Okay, so that's friction loss. So over here you have pressure drop, change of pressure. This is density. That's density. Rho is density. That is velocity change. Sorry, that's let me. Okay, that, oh dear. What have I done? Let me get rid of this. Okay. Let me undo. Let me start all over again. Okay. Okay, now this is change in velocity. That's a change in pressure. That is density. This is change in height. Okay, I just mentioned about friction loss just now. That is shaft work. And that is mass flow rate of your fluid. It's mass flow rate of your fluid. So when there is zero friction loss and there is no shaft work is zero, that equation will be converted to the Bernoulli equation. This is known as Bernoulli equation. It's the very simple equation that has only pressure drop, difference in velocity, and a difference in height. That is Bernoulli equation. That's the easiest. Okay? I need to point out to you guys, these three equations, they are only valid for incompressible fluid, liquid. Okay? They are only valid for incompressible liquid. You cannot compress the fluid. That means it's liquid. And there is no reaction. There is, if there's reaction, you cannot use that equation. And it's supposed to be steady state. And what else? That's more or less the restriction. Okay, so you have Bernoulli equation. So most of the time you'll be looking at Bernoulli equation. Okay, let's go to the next slide. Okay, this is one example. Let me get my iPad ready that we're going to look. Before that, I would like to do a simple example. I'm going to stop that. Yeah, I'm going to share with you guys my iPad. So far, any question? I'm not showing my video because I got flu, so I prefer not to. Okay, guys, This is from my iPad. Over here, I have written down the equation for Bernoulli and also the top equation for the mechanical energy balance. I already explained to you guys what the symbols are. Okay, when you look at this type of questions, or you look at this type of problem, you need. Okay, why is there a sound effect? Okay, you need to give two location to your diagram. The first is the equation position number 1, and the second is the position number 2. Normally, you have the inlet and outlet position or on the surface of the liquid. You normally place, for example, position number 1 on the surface of the liquid and position number 2 at the outlet of the pipe. Okay, so in this case, the diagram that I have, they are just two pipe lined. So there's no liquid surfaces. So I have only the inlet and the outlet. Inlet as the position 1. Position 2 is the outlet. Okay, let's ouch. And now, this is one example. Your volume coming in, the volume coming in is 20 liter per minute into that pipeline. It's water. It's water. So you should know the density of water. The density of water should be 1000 kilogram per meter cubic. Okay, that's the density of water. The diameter of the pipe changes from position 1 to position 2. At position 1, the diameter was 0.5. The diameter is 0.5 centimeter. But at point 2, the diameter is 1 centimeter. Now, that point 1, this is not really inlet. It's not open to the surface. I mean, it's not exposed to the environment. Position 2 is exposed to the environment. So the pressure at position 2 is 1 atm. The question is, what is the pressure at point 1? Okay? So if you have the equation for the mechanical energy balance, which I have over here, you are not given the friction loss, so you're going to assume that is 0. There's nothing moving, no turbine, no pump in our. I mean, there's a pump here, but there's no. We're not going to look. It's not given. There's no work given, so you're going to assume that there's no shaft work. Okay. So all we have is just the first 3 terms. That is your Bernoulli equation. So we're going to write that over here. Everything is equal to 0. That is your Bernoulli equation. Okay. You need to, how are we going to solve this problem? You're going to solve for pressure P1. How are we going to solve this, guys? Anybody? 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 Any idea? Nobody? No response? Okay, I'm not mute. I'm not mute. I'm still, you can still listen to me. Any idea? Okay, let's look at it. Okay, you have this equation. Change in pressure with density. Change in velocity, square over 2. Change in height equals 0. Let's look. Is there any difference in the height? Okay. Is there any difference in the height? There's not. Oh dear, I forgot to write down. What's the height? What's the height? There should be a height there. I forgot what's the height. Oh dear. Let's just put a value. Let me see whether I have the example over here. If I have the example here, that would be better. Okay, let's see. Let's put a value of 2 meter, for example. I don't have the problem with me. Just let's the height be not 2 meter, not centimeter. Should be 2 meter. 2 meter, the height. So that means the difference in height you can calculate. Okay, now you have 2 positions, Z1, that's Z2. because you need to calculate the difference in height. If you give a position of Z1 equals to 0, then Z2 should be 2 meter. What is your basis, guys? Anybody? You need to have a basis.
The volumetric.
Okay, that's the basis. Okay, what is your reference point? Even though I'm not calculating reference enthalpies here, what is your reference state? What's your reference state? You can choose one of the or two, the first location as your reference state or the second location as your reference state. So let's say we choose the first location. So let me write that over here. Reference state. You still need to have a reference state. Your reference state is low. For example, okay, let's choose. I don't like the reference state to be in position 1. Why? Somebody give me a reason why it would better not to have it at position 1.
No pressure mentioned.
Sorry?
In point 1, there's no pressure mentioned.
Okay, thank you, Muhammad Ikmal. Okay, so better to have it at point 2 because you have the pressure mentioned. Okay, so let's choose reference state at position 2. So that means pressure equals to 1 atm and liquid water. Location, height equals to 2 meter. That's what you need to specify. Okay, your basis, you already mentioned it. So that's your reference state. It's no longer about where you get the data from because we're not talking about enthalpy anymore. Okay, so now let's look at our difference in height. Difference in height, your gravitational acceleration, second square. Okay, difference is always Z2 minus Z1. That is different in height. Okay? So Z2 just now, if we look at the diagram, is 2 meter. Z1 is 0. So Z2 is equals to 2 minus 0. Okay, that is in meter. So your answer will be, if you calculate that, I don't have the solution, meter square per second square. Okay. Somebody give me a value. I really don't have the answer for that. This is not an example from your textbook, so I don't have the answer. I managed to calculate 19.62. Did you manage to get 19.62?
Yes.
Yes, Doctor.
Thank you. Okay, that's the unit. So next, we have a change of velocity square. But we are not given the velocity. We're not given the velocity. We're given the volumetric flow rate. Now, the volumetric flow rate is given. We're not given the velocity. So how are we going to get the velocity then? Anybody?
The cross-sectional area, Doctor.
Good. Okay, so I'm going to erase this. You need to find the cross-sectional area, and from there we can calculate the velocity because your velocity, the unit is meter per second, is equals to, you are given the volumetric flow rate, that is meter cubic. You need to change the liter into meter cubic, for example, per second. You need to get it in meter per second. That means you need to divide it by the cross-sectional area, which have a unit of meter square. So that will leave you with meter per second. So in order to get velocity, you change your, first thing first, we need to change your volumetric flow rate from liter to meter per second. So we have 20 liter per minute of water. So that's 20 liter per minute. 1 minute, 60 seconds, and 1,000 liter 1 meter cubic. So that will be in meter cubic per second. So if you divide that, let me calculate the value. 20 divided by 60 divided by 1,000. I got 3.33 times 10 to the power negative 4. 3.33, I don't have enough space. times 10 to the power negative 4. Did you manage to get the same value, guys?
Yes. That.
Okay, so that is, sorry, okay, that is meter cubic per second. I don't have enough space to write that. Meter cubic per second. Okay. Next, we need to calculate the velocity. So we're going to use the equation velocity is equal to volumetric flow rate divided by cross-sectional area. Oops. So, is there a sound effect? Okay, let's get that value just now. That value is 3.33 times 10 to the power negative 4. 333 times 10 to the power negative 4. I'm not going to write the unit because we know what unit we're going to get. Okay, cross-sectional area is pi over 4 times by the diameter. So if you want to get the velocity at location 1, so you'll be looking at the diameter at location 1. So the diameter at location 1 is 0.5 centimeter. That's 0.5. Oops. 0.5 at location 1. Okay, so let's go back to our third page, fourth page. That's 0.5 centimeter times 10 minus 2 square. That's your cross-sectional area. So you should be able to get your velocity meter per second. I'm afraid I might not have enough space, so I better write over here. Okay, that's U1. So if you want to get U2, you repeat the whole thing, but with a different diameter, because your diameter at the outlet at location 2 is, let's see, what's the diameter? The diameter is 1 centimeter. So divided by the cross-sectional area, 1 centimeter, you should get a value for your velocity from this calculation. Okay, so let's calculate. Somebody just left, is it? You check your calculation whether it's the same like mine. I managed to get 16.996 if I round it off. Did you manage to get the same, guys? Is it the same like mine? Oops. Any
Yeah.
plans?
Yeah.
Thank you. Can you give me the second velocity, please? Still calculating. Anybody give me a value, please?
4.24.
Sorry?
4.24.
4.24. Thank you, Muhammad Ikmal. Yeah, meter per second. I don't have enough space to write the unit. So if you write down the difference in velocity, that will be 1 over 2 u2 squared minus u21. So u2 2 is 4.24 square it minus the first velocity at location 1. To square that, your answer should be having a unit of meter square second square, because the unit for velocity is meter per second. So what's the answer? Calculate for me, please. So far, we managed to calculate the difference in height. We have that, oops, we got that value as a difference in height. Okay, we got that in meter square per second. Now we calculate the difference in velocity. They're also the same unit, meter square per second. So what's the answer, guys? I really don't have the answer because I haven't done the calculation yet. Not sure what's the final answer going to be. Let me, since I'm waiting for you guys, let me also do the calculation and see whether we get the same value. Oops, I got negative. Did you manage to get negative? I got negative. 143.83. Did you guys get the same value? Did I get a wrong value?
Same value, doctor.
Same value, thank you. Thank you, because I need somebody to double check my calculation, because I can just get a wrong value, but since okay, good, I did that calculation twice. Now let's look at the original equation, the Bernoulli equation. The Bernoulli equation, this is the Bernoulli equation. Okay, we have done that part, we have done this part. Now we are left with this difference in pressure. And let's solve for the difference in pressure then. Let's just difference in pressure is equals to, that's the density of water, 1000 is equals to your, if you bring it over to one side, the whole equation to one side, you bring this whole thing, you bring this whole thing to the other side, then you will be able to solve for the pressure difference. So let's do that. We have negative, we become positive for the difference in velocity, and the difference in height just now, which is that 19.62. Since it's positive, it becomes negative 19.62. But I hope I get it right. And 19.62. Okay. So your pressure difference is going to be P2 minus P1, and P2, is going to be, is given. P2 is given. P2 is 1 atm. That is P2. Okay. So since you are using the unit of meter and second, you need to change that pressure from 1 atm to, in terms of, we're having a unit of meter also. Meter, something with a meter in it. So 1 atm, if you look at the conversion unit at the back of, at the front page of your textbook, in terms of pressure, let's have a look. Pressure 1 atm is equivalent to, what is it? 1.01325. The unit is times 10 to the power of 5. The unit is Newton meter square. There's a square there. Yeah. I need to erase this so that you will not be confused. Yeah, there's a square there. Newton meter square. That's the conversion in from the first page of the cover. That's the pressure different. The conversion for pressure. So I need to use that unit in the calculation, but since I need to get an extra page here. Let's see. I need to get an extra page. Let me insert one extra page. Okay. Yeah, that's the previous page. So now I'm going to just erase some part of it because I need the final equation there. I'm not going to erase the whole page. I could erase the whole page, but I'm not going to do that because I need that final part of the solution. Okay, now let me bring this to the top. Oops. Oops. Mine cancel, sorry. Okay. No, sorry. Paste. Okay. Now, the unit that we have, let's change this first to get the difference. What is the difference? And then multiply by 1000. 134.83 minus 19.62 and multiply by 1000. Your answer will be 115.21. That unit is meter square second square. You need to change it. Sorry, I forgot about the temperature. That's the answer, right? But now I need to change that to in terms of pressure. So that's the answer so far, but we haven't get the change in pressure. So let's do this. P2 is given. P2 is 1 atm. So P2 is going to be, just now the value is 1.01325 times 10 to the power 5 minus P1, that's equals to 115.21, but you cannot stick with that value because you need to get it in Newton meter. So how are we going to do that, guys? Because this unit over here is Newton. What was the unit now? Newton meter square, is it? Let's check. Nobody responding to me. Okay, Newton meter square. Yeah, that's the unit. That's the unit. So we need to get it in, everything must be in Newton meter square. Get this unit into Newton meter square.
Doctor,
Yes?
from the formula, do we need to divide by 1000, right, for the change in pressure?
Yes, that's the the density.
Okay.
Yeah, I already multiply it. Is it, did I get the right answer, guys? Check. Let's see. Did I get it right? 134.83 minus 19.62. Yeah, divide time by 1000. Should be times 10. Okay, sorry. That's right, isn't it? It's 21. Okay, sorry. So that's comma 10. Okay, that's the answer. Now, how to get this 115,210 meters square to Newton meter square? Use your conversion factor. Okay, let's look at the how to get it, guys. Anybody? Anybody? You can look at the example in your textbook. There's one example in your textbook. Let's have a look. Example 7. Where is it? Okay. Okay, 1 Newton is equals to 1 kilogram meter square. Yeah. And let's see. Why am I not getting it? Somebody? Any idea? Anybody? How to get it? It's meter square second square. But your pressure is in Newton meter square. Over here, if we convert, we still will not be able to get it because 1 kilogram, 1 kilogram is still there. So how to get it? Anybody?
Doctor,
Yes.
after we multiplied by the density, even the unit must be written, right? Okay.
Oh yes, thank you very much. Thank you very much. There is a kilogram in the density, right? Guys, there is a kilogram in the density. So now let's redo this because I forgot about the density part. Let me erase this first. I forgot to convert. Okay, let's do this. That is 100 and this, what is the answer just now? What's the answer just now? Sorry, can you give me that value just now?
115.
115.2, isn't it?
210.
210, okay. That is meter square. No wonder there is a 10 kilogram there. Now, your density is 1000 kilogram per meter cubic, isn't it? That density. When you bring it forward, you multiply it. Okay, so now you are left with this whole thing change. Cancel it, that's become 1. Okay, so you have 115.21 kilogram second square meter. So now you need to change it from that unit into Newton because your pressure is in Newton. So 1 kilogram meter second square is equals to 1 Newton. This is the conversion that we have been doing, we have been using so far. You cancel your kilogram, cancel your second square. Now you have, your answer is going to be Newton meter square, which is the unit for pressure. And that whole thing is equals to P2 minus P1. You need to find P1. So if you want to find P1, you need to rearrange that equation so that P1 be on the other side. Yeah, so you need to rearrange this equation so that P1 is going to be on the other side. Or it doesn't matter. You just write 1.01325 times 10 to the power of 5 minus P1 equals to whatever answer you managed to get for that calculation just now. It's still 115, isn't it? Because this 1:1. So now what is P1? P1 is equals to 1.01325 times 10 to the power of 5 minus 115.21. So that's your final pressure in having a unit of Newton per meter square. That's the unit of your P1. Thank you very much. That was Iqmal just now for pointing out that there's the density here, which is kilogram per meter cubic. We need to put it over here so that we cancel off the meter square and we end up with per meter. Any questions? I forgot about that. No wonder there's a kilogram. Anybody? Any questions? That's how you calculate the pressure, because the question asks for a pressure at point 1. The pressure at point 1. You're given the pressure at point 2. Point 1 is at this point. You decide where you're going to put it. So point 1 is there. So you should assign your location, which will make your calculation convenient. Any questions? Any questions, guys? Anybody? Everybody? Anybody? Everything clear?
Actually,
Yes, sir.
I got negative for P1.
Negative? Negative?
Yeah.
Negative? Cannot be. Because this value is bigger.
Multiply by 1000 for that.
Why multiply by 1000?
The density part.
Okay. Times 10 to the power of 3. Times 10 to the power of 3. But still, cannot be negative, isn't it? This is times 10 to the power of 5. This is times 10 to the power of 3. Times 10 to the power of 3, isn't it? 5 minus 3 cannot be negative, isn't it?
No, doctor, it's 1.15 to the 10 power.
Yeah, it's 1.01 something times 10 to the power of 2 something. Should be positive, cannot be negative. Because this is 3, this is 5. The bigger value is the one being deducted, the smaller value is being deducted from a bigger value. Should be positive, not negative.
No, doctor, actually the one on the right is bigger.
Sorry?
The one on the right hand side is bigger.
The one on the right hand side is bigger. One on the right hand side is bigger. Okay. I'm 10 to the power of 5. How could it be the one on the right hand side is bigger? The one on the left hand side is bigger, isn't it? I'm 10 to the power of 5.
No, doctor, because it's 115 to the 10 power.
Okay. Times 10, 1.115. It's negative?
It cannot be negative.
You get a negative value. Everybody get a negative value. Okay. That means the pressure is negative. I must have got a very, very bad example to show you guys. Because of the height. I must have shown you guys a very bad example because I don't have the value of the height just now. The height, I don't have. Over here, I don't have the height. I just put a value there. I think that messed it up. The height really messed it up. Yeah. Sorry guys, but it should be, the procedure is the same. The procedure is correct. It's just that because of the height, it's somehow I gave you a very bad value for the height. Now we get a negative value. Let me see. Anybody did anything wrong with my calculation? Okay, that's the difference in this is U2 minus U1. That's correct. And I don't have the answer. That's why I don't know whether we're going to get negative or positive, because I'm just put something there. And let's see, we have 1000 ratio difference. And unfortunately, we get a negative value. It shouldn't be a negative value actually. Somehow I got I messed it up when I gave you a height that is not a suitable height. The procedure is correct.
In this case, the P2 should be higher than
P2 should be higher.
if the height is this much.
Yeah, if the height is that high. P1 should be higher than P2. P1 should be higher than P2. P1 should be higher than P2. Should be, cannot be negative. Or else there's no way it's going to flow. Logically, P1 should be higher than P2. For a fluid to flow, the pressures, for inlet, the pressure should be higher at P1, or else it cannot flow. Isn't it?
That then is correct.
Sorry?
Then it's correct.
Yeah. P1 should be higher than P2. I'll get back to you guys on that maybe tomorrow. But right now, I will check back on it. Okay? Because I'm not going to spend too long on that, because we need to
Can I
look
see the
at.
next slide, Doctor?
Sorry?
Can I see the next slide again, please?
I could hardly hear you.
Can I see the next slide again, please?
Next slide. Which one?
The
This one.
next page.
This one? Is that it?
The other one?
The
The
one?
last one. though.
Yeah, last slide. Yeah, I made a mistake somewhere. The pressure is always 0.2 minus 1. Because 0.2 is supposed to be lower than P1.
So that means it should be P1 minus 1.01. then.
What did you say, Dina?
It should be P1 minus 1.01, right?
P1. P1 minus
1.0.
1.0. Why minus 1.0? I don't understand.
Because initial is higher, right?
P1 should be higher, or else it cannot flow. P1 should be higher than P2, or else it cannot flow. That's logically. Yeah. So, but because we have the equation delta P, if you look at the problem, is always out minus in, or 0.2 minus 1. It's always like that. It's always 2 minus 1. Yeah, so I'll get back to you guys on that. Did I make a mistake somewhere? I'm not sure. But I get back to you guys on that. P1 should be higher. There's one example. Let's look at example 771. It's almost the same. And let's get back to let's look at this later on. We're going to look at another example. This is example 711, the same as
Doctor.
yes.
So delta P is 115, right?
Yes. Times 10 to the power of 3.
Then delta P should be negative.
Delta P should be negative.
Yes.
Why is it negative?
Because P1 is higher than P2.
Okay, hold on. Let's look at example 771. Then we will go back to this example later on. Yeah, I don't want to.
If you would put negative to 115, then it would be correct.
How could it be negative? Let's go back out to our, okay, since you insist on this. Okay, look. Okay, this is negative here, right? Yeah, that's negative. And when you bring it inside the equation, when you put it inside the equation, that equation is over here. That's negative. Let me put that value 134 point. What that value is now? Let me write it. 134.83. Okay. 0.83. Okay. And the other equation is our height. That's positive because we denoted it to be higher. So that's positive. 19 point, what's the height just now? 19.62. Okay. 19.62. That's positive. So when you bring this over, that negative become positive. This negative, when you bring it over to the other side, become positive. This positive become negative when you bring it over to the right hand side. So that's what we did, isn't it?
Oh, okay. So that makes it positive.
Yeah. Okay. So let's stop looking at this problem. We need to look at another example. 711 is which is very similar. Maybe we can see what's the problem with that example once we solve for this example. Okay. Now let me enlarge it. Okay. Have a look. Not this one. Sorry. This is quite wait, another one. Sorry. Not this one. 771. Wait, 771. Yeah. This is it. 771. Yeah. Almost the same. Almost the same. Look like the same, but a different set of questions. Different set of values. Sorry. You have water again. Fluoride. Oh, this is it. This is the one that we did just now, isn't it? Aha. Look. Different height. This is the one that we did just now. I'm sorry. This is the same example that we did just now, except that just now I gave you 2 meter. Okay. This is exactly that problem just now, except the height is a different height. It should be 50 meter now. Okay, let's did. Okay, let's look at that problem just now. If you look at this problem, our delta U square is equals to divide by 2 just now. We get minus 134, isn't it? 134 point, what did we get? The example just now?
83.
83. But if you look at your textbook, that value is 135.5. Now, where's the problem from that previous example just now? 134.83. When we did the calculation, we get one. We did the velocity just now. Okay. If you check your answer with the textbook, they rounded this off equals to 17 inside the textbook. This one is 4.24, so we got it right. So okay, that we got that right. So I'm looking at the textbook right now. Yeah, not that example, sorry. I got the wrong one. This one. Okay. We got that right. So the height different from your textbook. The same problem from your textbook. The answer is 490. The answer is 490. Why 490? Because of this height. Okay, so let's do this. 9.81 times by different in height. Z1 is equals to 0. Z2 is equals to 50. That's 50. So that's 50. They managed to get. The answer is 490. Do you get that? Calculate, please. Please calculate. 9.81 times by 50. Yeah, 490.5. And that unit is meter square per second square. Same here, meter square per second square. Yeah. Same calculation, except that the height now is actually 50. I forgot about that. That this is the same example. Okay, so now if you do the calculation for the pressure drop is equals to P2 minus P1 divide by 1,000. That will be 134.83. For this example, we have minus 490.5 for this example because of the higher height. Okay, so when you solve for it, now you multiply by 1,000, your P1, this value is equal to 1.01325 times 10 to the power 5. What is your answer for P1 in Newton per meter square? We have dealt with the unit before, so we should have no worry with the unit. Do I need to calculate multiply by something times 10 power of 3? This is 10 times power of 3. There, that's the density. What did you get for P1? Anybody? Did you get the same value for as the textbook times 10 to the power 5? You get that value? Calculate please. Yes, thank you, Charisma. So the problem just now, the height was too low. Okay, that's why we get a negative value, but it doesn't make sense to get a negative value, isn't it? It doesn't make sense to get a negative value. P1 should be greater than P2. For this problem, P2 is 1 ATM. So P1 is about 4.5 ATM. 4.56 ATM. We solved that problem just now that we got negative because the height is too low. It's only 2 meters. Any question, guys? Would you want me to repeat this for this example? Or is it you already managed to get, you understand it? Because I'm using the values from the previous example, except for the...
Doctor,
yes,
can you repeat?
the whole calculation.
I mean, if it's possible.
Okay, thank you. Okay, I'll do that. Let me clear part of it. Oh, dear, I erased that. I should not have erased that. Okay, let me, what is written 20 liter per minute, that's 20. I'm having problem here because this is too fine. Okay, that's 20 liter. Oops, undo that. That's 20 liter per minute. Okay. Okay, let's get the value from, let's do everything all over again. We know that we have this Bernoulli equation. Yeah. Why we have Bernoulli equation, not delta G. Why we have Bernoulli equation? Because there is no friction loss given. There is no shaft work. I mean, there's no pump, anything. But that is that diagram I did before. I have a pump there. I should not have drawn the pump. This is just a different flow inside a pipe, a straight pipe. No pump, no turbine. Okay, so there's no shaft work. So now let's calculate the cross-sectional area first at 0.1. Find we denote that as 0.1, that as 0.2. Okay, pi over 4. Your diameter at 0.1, 0.5. I'm repeating a whole thing all over again. Okay, so you should get an answer. What's the answer, please? Let me calculate also. You guys also calculate so that we can check each other whether we come up with the same answer. Yeah, I managed to get 1.963 times 10 to the power of minus 5. That is meter square. You guys, did you manage to get the same value? Guys, calculate it, please. Cross-sectional area for number 2, location 2, pi over 4. We did not calculate this just now using that previous example, but this is 1 centimeter. Why not just calculate it anyway? Square. 0.5 just now. I'm going to double check my calculation. square. I forgot the square just now. It was divide by 4. Okay, I got the same answer. Now, 1 times 10 to the power of negative 2 square it times the pi divide by 4. I managed to get 7.854 times 10 to the power of negative 5 meter square. Okay. That is your surface area. Now, when you want to calculate the velocity at point 1 is equal to the volumetric flow rate divided by the cross-sectional area at point 1. Your volumetric flow rate is the same at both points because the same fluid is flowing. There's no, I mean, it's inside the pipe. So it's the same fluid is flowing. So your cross-sectional area just now is 20 liter per minute. We did convert this 20 liter per minute into per second. What did we get just now? 20 liter per minute change into meter cubic per second. What did we get just now? Did somebody jot it down? I think it was 3.33, is it? Anybody give me the answer? Somebody? Times 10 to the power what?
Yes, Doctor. 3.33
333 point times 10 to the power of, sorry?
minus 4.
Minus 4, thank you. I need you guys to help me with this. Okay, or else I need to go back and forth with my with this iPad. So this will save lots of time when you give me the value. Yeah, that's meter cubic per second. You divide it by the cross-sectional area, 1.963 times 10 to the power negative 5. That's meter square. So you will cancel off the meter square. You will leave with only 1 meter. So your answer will be in meter per second. And we did manage to get an answer just now. What did we get? I think we got 16 point something, 16.9 something, isn't it? What did we get just now?
9.6.
9.6, thank you. Okay, that is your velocity at location 1. So you do the same thing for location 2, the same volumetric flow rate, except that now your diameter, cross-sectional diameter, sorry, not diameter, your diameter is changed, so your cross-sectional area is going to be different. That's at point 2, at location 2. Okay, so if we put the meter cubic per second, that's meter square. You cancel that, you end up with meter per second. And I sure we got this value, 4.24 meter per second, the same as the textbook. Okay? That's how you calculate your velocity. So now what we have to do is calculate the difference in velocity. Okay, 1/2, the difference will be u at location 2 is always 2 minus 1. Whatever you're looking at pressure drop, or you're looking at height different, or you're looking at density, velocity different, it's always 2 minus 1. Okay, so that's over 1/2. Your final velocity 4.2, not your final, that's your outlet velocity square, minus 16.96. I'm repeating the whole thing. Yeah. So your answer just now, we managed to get it. The same answer as the previous example. It was negative 134.83, is it? What we get just now? Did you get this value just now?
Yes, Doctor.
Yeah. Okay. Okay, that's the first part. Now let me. Okay, that's the first part. Any question on this? Let me erase that. Get it better. Let me write it. Okay. Minus 134.83 meter square second square. Okay. Now let's look at our next. We have done this. We have done this. Oops. Oh, come on, not looking. We've done this. Now we're going to look at the pressure, the height. We're going to look at the height. It's G delta Z. Z2 minus Z1. Okay. For this example, let's go to our diagram. For this example, the height Z1 is going to be 0 because it's better to have it 0. Then the higher height will be Z2 is going to be 50. If you're if you're going lower, then your value will be negative. In this case, you start at 0 and you're going higher up, then your value will be positive. This 50 is positive. Okay, so now let's calculate that. Z2 minus Z1 is equals to 9.81. I'm not going to write the unit there because we already know what the unit is going to be. 50, let's hit 50 minus 0. So that answer, if you look at the textbook, is 490.5. 0.5, thank you. And that is in meter square second square. Okay. So let's go back to our equation. Our equation, you have this equation, Bernoulli equation. Yeah. So if you write down the value, that the P over density minus, what did we get just now for our ratio of the velocity difference, minus 134.83, minus 134.83, and we just got that value just now, 490.5. The whole thing equals to 0. I'm going to solve that problem, to continue with the calculation on the next page. That is delta P over 1000, that's the density of water, minus 134.83 plus 490.05 equals to 0. So if you bring everything all over to the right hand side, that becomes positive. Minus 490.05 and multiply it with 1000. The unit, will cancel off. Or if you want to do the to show the unit, let's show the unit then. I need to write smaller then. Let me. If I'm going to show the unit, I need to have space. Need to rewrite. Let me erase this because I need to rewrite the unit. 134.83 minus 490.05. No. That's meter square, second square. And I have 1000. The unit for 1000 is kilogram per meter cubic. Right? So you cancel that, you end up with 1 meter there. So your unit is going to be kilogram per meter second square. So when you multiply that, what the answer do you get? Negative, isn't it? Because a negative 490 minus 134, it will be negative. So your answer will be negative. What's the answer? Let me calculate too. 134.83 minus 490.05. And the answer is negative 355 times 10 to the power of 3, that's 1000. The answer is negative 355,220. Yeah, that's the answer. So pressure drop is equals to P2 minus P1. Your P2 is given to be 1 atm. 1 atm, if you convert that into Newton meter, 0.1325 times 10 to the power of 5 Newton per meter square. Oops. So if you substitute that for P2 over here, solve for P1. But remember, you need to change this unit also so that it will have the same unit as Newton meter. So let's go to the next page. Oh, I still have some more page here. Oops. Yeah, okay, let's write down 1.0. Let's change that unit first. I'm going to change the unit minus 355,220 kilogram per meter second square. I'm going to change it into Newton. So 1 Newton is equals to 1 kilogram meter second square. Okay, so that's the unit that we have been using so far. We cancel the kilogram, we have the second square, you cancel, we end up with a unit of Newton meter squared. So what's that answer? My negative, still the same, isn't it? Same value. Same value, because it's just 1:1. Okay, so what we've got to do next is solve for P2. P2 is P1 times 10 to the power 5 minus P1 is equals to negative 355,220. That's the answer. So now P1 is equals to 1.01325 times 10 to the power 5. Bring this over, become positive. 355,220. Is that correct, guys? Have a look at the sequence. I bring this over to that side, become positive P.
Yes, yes, doctor.
Yeah, I bring that over. Yeah. Okay. So P1, if you calculate it, the answer will be Newton meter squared. So if you calculate that, let me do the calculation.
101.
1.680.22.
101,680.22.
Huh? 1.01?
101.
101.
680.
Cannot be. The answer in the textbook is 4.56 times 10 power 5. Yeah.
Yes, I got this too, doctor.
Which one? The same.
The same as the textbook says.
Same as textbook. Okay.
Yes, yes.
Okay. Should be the same as textbook. Please check your calculation. It should be 4.56 times 10 power 5. Should be. But this is 1, 2, 3, 4, 5. That is, if you change this, let me change that. 3.55. 3.55 times 10 to the power 5. Okay, so 3 plus 1, 4. Should be. Okay, guys, any questions? So that problem and the previous example I gave you guys is actually the same example. I forgot about the height. Unfortunately, I gave a value of 2 meter and that will create a problem. When the height is not high enough, it creates a problem. So let's go back to our first page. Yeah. Now, this is going to be P1 is equal to 4.56 ATM. This is 1 ATM. It has to be higher. P1 must be higher than P2. Why? Or else it cannot flow. The pressure is the one that is pushing the liquid to flow upward. P1 must be higher than P2. That's why I was trying to figure out just now why we managed to get a negative value. I don't understand why. Because P1 must be greater than P2. Maybe the height was too low. I don't know. But definitely, it should not be a negative value. It should not be less than P1. It should be greater than not less than P2. It should be greater. P1 should be greater than P2. Any questions? Guys?
It's clear, doctor.
Thank you. Okay, let's look at another example. The one that I asked you guys to convert the unit. Where is it? Where is it? That is Siphon. Yeah. This is the one that I asked you guys to convert the unit. Did you guys convert the unit, guys? Did you guys convert the unit? Let me see whether I have the conversion with me. Okay. I converted the unit. The density after conversion, this is density. Converted the unit because I don't like English unit. The reason is it would be easier to deal with SI because we already know the conversion. I mean how to convert from kilogram Newton meter to the unit that we've been using. Check whether my answer is correct. Okay, guys. The frictional force here, you have frictional force. frictional loss, sorry, that's F. F is given, that is the value. And after I have converted it, I managed to get this value, 2.3912. Did anybody converted it beforehand? And check your answer with mine? Yeah, let me erase that a bit. It's Newton meter kilogram. Did anybody converted the unit, please? Can check with mine. Okay, the gallon of 5 gallon. 5 gallon, that is the volume, 5 gallon. When I converted it, I managed to get 18.927 times 10 to the power of negative 3. That is meter cubic. Okay, when I converted it. Next, what do I need? Okay, Z, the height, 2.5 feet. When I converted that, that become 1.905 meter. Oops. Yeah, 1.905 meter. What else? P1, P2. Okay, the pressure should be 1 atm. Yeah, P1 is on the surface. That's P1. This is also at the outlet, right before it at the outlet. So P2 is also at 1 atm. If you're going to solve this problem, what else? What do you need to find? You need to find how long, the time it takes to empty the tank number 1, so that everything transfer to tank number 2. Okay, let's look at this problem. You have pressure different, you have velocity different, you have height different, you have the friction loss is equals to shaft work divided by mass. That's the final equation. You don't have any moving parts, so this part will cancel off. So you end up with just the first 4 terms. Pressure different. Is there any value different in pressure, guys? Anybody? Anybody? My God, I don't have any response at all. Are you guys so tired that you can't answer? Hello, am I speaking to myself?
Yes, doctor, we are here. Same.
Same. P1 equals to P2. Why? Because P1 is on the surface of the liquid. Okay, it's a pressure of 1 atm. P2, which is just at the outlet of the pipe, is also at 1 atm. So there's no pressure difference. P1 minus P2 minus P1 equals to 0. Because there's no pressure difference. Both of them is at the same pressure. Okay? So now, what is U1? U1 is on the surface. Which is on the surface? U1 is equal to 0. Why is U1 equals to 0? Because the surface area of the surface is bigger than the surface area of the size of this pipe. The surface is stationary. The surface is not moving. I mean, it's not that it's not moving. The surface is not, there's no velocity there. U1 is equal to 0. Okay? The surface area of this surface is bigger than the tube surface area. So there's no, the movement of the liquid is not moving that much. It's only to 0. It's equal to 0. So U1 equals to 0. U2, you don't know. You don't know what is U2. That's the value you need to calculate. Once you manage to get U2, then you can find the time. So let's calculate, let's see. How are we going to solve this? Anybody? Any opinion? Any suggestion? Okay, now I just remember something. The height just now is 2.5 feet. Where are you going to put your Z1? you could put your your starting, your reference. What is your reference state? Before you do anything, what is your reference state? Guys, it would be better to choose 0.1. Why 0.1? Because you can write 0.1, u1 equals to 0. You have the velocity there. u2, you don't have the value. The velocity at 0.2, you don't have the value. Right? You need to find that velocity at u.2. It's not given. So since u2, the velocity at 0.1 is given, you choose that as your reference state, 0.1. And it's liquid water. And you're going to denote Z1 is equals to 0. You start on the surface 0. So that means you're going downward. So Z2 is equals to negative. You're going downward. Z2 is going to be negative. Why? Because your fluid is going downward. The height is going downward, so your Z2 is going to be negative 1.905 meter. Okay, let's look at this. U1 equals to 0. P1 is equal to 1 atm. That is your reference state. And what is your basis? What is your basis? Your basis is going to be 5 gallon. That amount of water, 5 gallon of water. You need to write down your basis and your reference state before you can solve for, before you start solving for the problem. Okay, so now the G, different in height, is equals to G Z2 minus Z1. And since I'm using SI unit, if you're using the English unit, you stick with the textbook. I'm using the SI unit. So I'm going to multiply Z2 is going to be negative 1.905. Why negative? Because my starting point is at Z1. The liquid is flowing downward. So the Z2 is going to be negative. But that is in meters square per second square. Yeah, you can solve for that value. Next, the temperature, you managed to get that. The friction loss, we have the value for the friction loss. We need to calculate the difference in the velocity. So delta U square over 2 is equals to U2 square minus U1 square, which turned out to be 0. You need to know why it's 0, because that surface area is bigger compared to the pipe, and that surface is stationary. Yeah, is equals to U2 square over 2. So now I put everything inside the equation. So if you put everything inside the equation, you have, oops, now let me undo that. So this is your U2 square. You let me change color. Okay, that's okay, done. That's it. That's that value. Yeah. G, that value. F value, we have that given. That's the F value after you have converted it. So everything is there. Solve for your U2. Once you manage to get U2, you can solve for time. Because you already know what's the volume that you're going to handle. You got you have the gallon there. Remember, you have the 5 gallon. This is your 5 gallon meter cubic. So what you have to do is get your flow rate, your surface, with your area. You need to calculate. This is your U2. So in order to get your volumetric flow rate, this unit is in meter cubic per second. You have your velocity 2, which is meter per second. You got to get your cross-sectional time by cross-sectional area, meter square. So where is your diameter? Is there a diameter given? Is there a diameter given for your tank? Anybody? I can see the diameter here.
1 over 4 inch.
1 over
4 inch.
1 over
ID hose.
where I can see it here.
In the middle of
in the middle.
pipe, is it?
Okay,
Yes.
here, sorry. That's it. Cross-sectional area. Yeah. If you change that, you got to change it into meter. Change it into meter. So everything is there. You can calculate the cross-sectional area using the 1/4 inch, but change that into meter. Change that into meter. It must be in meter. So everything is there. Once you get this, put it, substitute it there. And once you manage to get your velocity, you should have the unit in meter cubic. Yeah. And what you need to find is time. Time is in second. So how are you going to do that? Anybody?
Divided by the cross-sectional area, the volume.
Divided by the volume. That is the 5 gallon is value. That 5 gallon. 5 gallon is meter cubic. This is also meter cubic.
Yeah.
Then you get the time. You cancel off meter cubic, you get the time. Okay? Any question? This is your volumetric flow rate. So your time will be the 5 gallon, change that into meter cubic, divided by your volumetric flow rate, which is meter per cubic per second. Your answer will be in second. You understand? This is the 5 gallon that is given from the solution, from the equation. Change that into meter cubic. That's the answer in meter cubic. And when you divided that by this flow rate, this volumetric flow rate, your answer will be in second. That is the time it takes to finish to completely empty tank number 1. You think you can get my explanation? Is that clear? You are just dealing with the same equation, except that this time you have the friction loss given. You have the friction loss given. Everything is the same, except that now you have the friction loss. The pressure difference is 0. Why? Because P1 is equals to P2. They are both at the same pressure. Any question, guys? We are about to finish today's lecture. Any questions?
Yeah, and doctor, why do you consider U1 as 0?
U1 equals to 0 because it's on the surface of your tank, and that surface area is much more bigger than the size of the pipe. The pipe is inside the tank. There's no movement on the surface. Okay?
Okay.
That's why it's 0. Any other questions? The U2 is the velocity allocation 2 is not 0 because liquid is coming out from it. Any other questions? You need to remember to state your reference state. Oh dear, I keep on. Sorry, where is it just now? Okay. You need to remember to state your reference state and your basis. You need to do that. But whether you are looking at mechanical energy balance or the previous energy balance that we were dealing with, you need to specify your reference state and the basis. You have to do that. Any other questions, guys?
No, doctor, it's clear.
Okay, good.
Doctor,
Yes.
sorry, the QR code, can you share it again? Because I was not able to scan it, in the beginning.
Explain what?
Can you share the QR code once more?
QR code. Okay. I will unshare. Sorry. Okay. Where is the QR code? Okay. That's it, I guess. Once you have scanned, I guess this is. If anybody have any other question before we ends today's lecture, any other question regarding that previous example? We will continue with more example on this mechanical energy balance tomorrow. Any other questions? Anybody? Wow, I managed to get 36 students. One person is missing. Any questions?
No, doctor.
Okay, I would suggest you look at example 772, the one that we just did just now. I converted the units. See whether you can come up with the same unit with me and check your answer. Once you have managed to get the final answer, convert it to the SI unit, to the English unit. Is it the same? Make sure that my conversion, the one that I just converted from SI English unit to SI is correct. You double check on that. You do the same calculation. as I suggested just now, and see whether you come up with the same answer once you converted it back to the English unit. Okay, because the solution is in English unit. I prefer not to use English unit because whenever you want to convert, for example, the pressure 1 Newton per meter square in order to get 1 kilogram meter second square, I prefer to use that conversion only. You can look at the solution inside the textbook. For that example, it's in English unit. You can use the same procedure is used, except that unit is in English unit. So it's a bit, because we're so used to SI. So when you use English unit, you need to adjust a bit. So it's still the same. Okay, guys, any questions? No questions? Okay, by now you should be able to do question number 3 of the assignment. This is more or less what is, question number 3 is all about. You should be able to solve it. But we'll be looking at more example tomorrow, inshallah. Okay, guys, thank you very much.
Thank you.
Thank you. See
Thank
you
you,
guys
Doctor.
tomorrow. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Welcome.
Thank you, doctor.